The Pythagorean theorem establishes the fundamental rule for calculating distance within a structured space. The equation is expressed as a squared plus b squared equals c squared. In this visual model, a and b represent the lengths of the two shorter sides meeting at a 90-degree angle, and c represents the hypotenuse, the longest side connecting them. The theorem dictates that the total area of the squares formed on the two shorter sides is mathematically identical to the area of the square formed on the hypotenuse. This relationship allows for the derivation of an unknown length provided the other two are known. While this is geometrically demonstrated here with a 2D triangle, its primary application lies in coordinate geometry. In data science and vector analysis, this logic is expanded into the distance formula. Computers use this to calculate the difference between data points in multi-dimensional space. For example, if an algorithm is analyzing customer similarity, it plots their behaviors as coordinates. It then uses this theorem to calculate the straight-line distance between them, mathematically determining how close or similar two different users are based on their data. The quadratic formula provides a systematic solution for finding unknown variables in nonlinear equations. It is used to solve equations in the form ax squared plus bx plus c equals 0. Here, x is the unknown variable, while a, b, and c are fixed numerical coefficients. The formula includes a plus-minus symbol, indicating that the operation splits into two distinct calculations, typically resulting in two valid answers. Geometrically, this formula calculates the roots, which are the precise coordinates where a parabolic curve intersects the x-axis. Because a curve loops, it touches the axis twice. This shape is the fundamental model for gravity-influenced motion in physics. In engineering applications, this calculates trajectories. If a projectile is launched with a specific velocity and angle, the quadratic formula determines exactly when and where it will return to ground level. It is also used in structural engineering to calculate the load-bearing curves of suspension bridge cables, ensuring the materials can withstand the tension required to hold the bridge deck. Euler's identity is defined as e to the power of I times pi plus 1 equals 0. This equation is significant because it unifies 5 distinct mathematical constants into a single relation. E governs continuous growth, pi governs circular geometry, I is the imaginary unit which allows for calculation in a complex plane, and 0 and 1 represent the fundamental arithmetic identities. Functionally, this equation demonstrates that exponential growth, when applied through an imaginary dimension, results in rotation rather than expansion. The term e to the I pi describes a semicircular rotation of 180 degrees in the complex plane, landing at the value of -1. When 1 is added to this -1, the result is 0. This relationship between circles and growth is the operating logic behind signal processing. It allows engineers to analyze waveforms. By using Euler's identity, complex signals, such as radio frequencies, Wi-Fi data, or audio recordings, can be decomposed into simple rotating sine waves. This makes it possible to filter noise, compress data, and transmit information wirelessly. The derivative measures the instantaneous rate at which a quantity changes. In standard algebra, one calculates the slope of a straight line to find an average rate. However, real-world rates fluctuate. The derivative calculates the slope of a curve at a single infinitesimal point. Visually, this is represented by a tangent line, a straight line that touches the curve at exactly one coordinate. The steepness of this line represents the rate of change at that exact moment. If the curve represents a car's position over time, the derivative represents the speedometer reading at that exact second. In artificial intelligence, derivatives are utilized in a process called gradient descent. When an artificial intelligence makes a mistake, the system uses derivatives to calculate the slope of its error. It determines the direction in which the error decreases most rapidly. The algorithm then adjusts its internal parameters to slide down that mathematical slope, effectively learning by minimizing the error rate. The integral serves as the inverse operation to the derivative and is the mathematical tool for accumulation. While the derivative divides a whole into instantaneous rates, the integral sums an infinite number of infinitesimally small quantities to determine a whole. Visually, integration calculates the total area found underneath the curve on a graph. By summing these infinite slices, it provides precise measurements for quantities that change continuously. If a graph represents the varying speed of a vehicle over time, the area under that curve, the integral, calculates the total distance traveled. This concept extends to 3 dimensions, allowing for the calculation of volumes for irregular objects that cannot be measured with simple geometric formulas. In medical imaging, such as CT scans, integration is used to reconstruct a 3D model of an organ by summing up the data from 2D cross-sectional slices. This allows doctors to visualize total accumulation of tissue or anomalies within the body.